everybody, and welcome to the first explainer video on this channel. I'm Jan, and today we will discuss when we can know in econometrics that we are estimating the true effect in a regression. In particular, we will speak about something you're likely familiar with from your university lectures, which is omitted variable bias. In short, assume that there is a variable omitted from a regression. Then the effect that we find for another variable that is in the regression is likely not the true effect of this included variable. How will we approach this? First, I will give you some classic examples of omitted variable bias to illustrate the concept. Afterwards, I will show you 3 ways to understand the intuition behind omitted variable bias, some of which you might not have seen before, followed by the derivation of the standard OVB formula. In this video, I will focus solely on the simplest case, which is linear regression with one variable. I have a supplement video that discusses OVB, omitted variable bias, when you have multiple explanatory variables. It works slightly different from the single variable case, but most of the intuition carries, obviously. I also have a video showing how 2 standard sources of endogeneity in economics, measurement error and simultaneity, can also be put into this framework. Finally, closely related to omitted variable bias is the so-called fundamental problem of causal inference. Check out my video concerning this issue here, or follow the link in the description. Would you be surprised if I told you that people are more likely to die after going to hospital than if they didn't? Do college graduates earn more than high school graduates because they went to college, or university as we call it in Europe? And did you know that countries with higher chocolate consumption win more Nobel Prizes? Those are all examples of omitted variable bias. Let's quickly look at which variable is omitted for each example and look for the problems that this causes before we look at how we can solve this issue. If we only compare people who went to hospital to those who didn't, we neglect that there is a reason why people go to hospital typically. They are in need of, for example, a surgery. A person with cancer surely has a higher risk of dying whether or not they went to the hospital. But most people with cancer live longer if they go to the hospital than if they don't. So here, the variable that we lack is the health of a patient. If you watch this video, then most likely you are a college student. Maybe it was clear to you that you will attend college, but for many it is much less clear. One input into this decision is how much you enjoy the kind of mental work that is required. The thinking, the abstraction. This mental work is also regularly required for high-paying office jobs, while it is to a much lesser extent required for the lower-paying manual jobs. This like or dislike for mental work is then our omitted variable. Finally, although you might want to justify your chocolate consumption with increasing your chances of winning a Nobel Prize, I certainly sometimes do, a closer look at the data probably suggests that it's mostly high-income countries who both consume a lot of chocolate and win a lot of Nobel Prizes. So if we put forward an alternative theory, it would be equally plausible that rich countries can buy a lot of chocolate and give a lot of money to research. So we miss the development status or the research funding of these countries. Now, what do all these examples have in common? We have an outcome that we're interested in, be it mortality, wages, Nobel Prizes. We consider an explanation for these outcomes. People die because they went to the hospital, they receive high wages because they went to college, they win Nobel Prizes because they eat a lot of chocolate. However, it turns out that there is another explanation for our outcome using a variable we didn't observe, which importantly also justifies the original relationship that we observe in the data. In fact, there are very neat graphs that we can paint for each of these examples, which show us a bit more intuition. So let's look at this now.
In our first example, illness causes both mortality and hospital visits. In our education example, liking mental work causes both college and earnings. Finally, in our Nobel Prize example, being a rich country increases both chocolate consumption and science funding in turn causes Nobel Prizes.
These graphs have a name, by the way. They are called directed acyclical graphs. I plan to create a video to explain this tool, but in the meantime, if you are interested in this concept, I recommend the book linked in the description. Now, let's put our intuition into something a bit more formal. Let's start with our standard linear regression model and stick to the example of chocolate Nobel Prizes. We have two regressions.
The first one is called the short regression. The second one we can call the long regression because it is longer than the short one, and that's really all there is to it. If you have not seen this before, then this is a good point to briefly pause the video and take a look at these equations. Note that our betas from the short regression do not need to equal the deltas from the long regression. In fact, this is the main problem with omitted variable bias. Why is this? Remember that in a regression, we try to explain the variable on the left-hand side, the Nobel Prizes, with the ones on the right as good as we can. Now, if we exclude the rich country variable from the right-hand side, as we do in the short regression, intuitively, chocolate will try to pick up the effect of being a rich country, since countries eating lots of chocolate are also richer.
Alright, so what goes wrong if we don't include a variable for the rich countries? We can look at three different approaches for this. A very neat one and quite famous, at least if you're an economist, is the omitted variable bias formula. But we will get two other approaches as well, and we will actually start with a different approach, namely the graphical way to represent this problem.
Right, so in this graph we plot the number of Nobel Prizes against the chocolate consumption. You should be aware that I've generated this data, so there's a real phenomenon that countries which consume more chocolate also win more Nobel Prizes, but there's not the actual data on this, there's just for illustration. Looking at this, it seems to be a very solid pattern. If a country has a high chocolate consumption, it also has a high number of Nobel Prizes that won. But what happens if we look at which development status these countries have? Now, the countries in blue are the developing countries, which likely spend less on science research, whereas the countries in red are developed countries, which spend a lot on science research and thus also have a higher number of Nobel Prizes. If we looked inside each country group, then actually we wouldn't think that there's any correlation between the number of Nobel Prizes and the chocolate consumption. It looks all over the place, really.
Let's go back to our previous directed acyclical graphs to get another way to look at it.
Now, in contrast to our previous attempt, we add numbers to these lines to quantify the impact of one variable to another. So the effect of eating chocolate on Nobel Prizes is delta 1 from the long regression, and the effect of being a rich country on winning Nobel Prizes corresponds to our delta 2 coefficient. You might be slightly confused why there's an arrow pointing from chocolate consumption to being a rich country. This arrow represents that you can predict whether a country is rich by the amount of chocolate it consumes, because the rich countries eat more chocolate. So if you see a country that eats more chocolate, then it's more likely to be a rich country. This arrow is not a causation error, the one with the 0.29 attached. So we see that 0, our delta 1 in the long regression, is the direct causal effect of eating chocolate on the number of Nobel Prizes a country wins. However, there's a backdoor which you can use to predict Nobel Prizes, which goes via chocolate to being a rich country, to the science funding a country gives, back to Nobel Prizes. So there are two ways how you can get from chocolate consumption to winning Nobel Prizes, which is one, you eat more chocolate, you immediately get more Nobel Prizes, or in a regression setting, you eat more chocolate, so you're more likely to be a rich country, you have higher science funding, and thus you get more Nobel Prizes. If you add these two paths together, that will be the regression coefficient if you regress Nobel Prizes solely on chocolate, i.e. our short regression.
If you write this down, then actually you will get a formula which looks very familiar because it looks like the omitted variable bias formula. Oh, we've just derived it in an entirely different way, which I find fascinating. In most stats or econometrics classes, you probably have not seen the previous two ways to describe the omitted variable bias, but only the famous or infamous OVB formula. So now let's have a look at deriving this.
As before, we have two regressions, the short regression and the long regression. The question is, how does beta 1 in the short regression compare with delta 1 in the long regression? You will probably remember from your stats classes the very nice formula for beta 1, which just involves scaling the covariance between Nobel Prizes and chocolate by the variance of chocolate. Now we plug in the true causal process, which is the long regression. You can obtain this formula quite easily by putting apart the sums in covariances, because the covariance is linear. Now you might think this actually looks much worse than what we've had before, but it's actually much nicer, because if we look at this, the first term is a covariance with a constant, which is always 0. Delta 0 doesn't vary, so it can't co-vary with something. It's constant. So the first term on the right-hand side is 0. A constant multiplying a variable can be pulled out of the covariance. So the second term is delta 1 times the variance of chocolate divided by the variance of chocolate, which cancels, so we are left with delta 1. Now, it becomes a bit easier if we do the fourth part first. We assume that the long regression is the true regression, the true causal process, so that eta and the variable chocolate consumption are unrelated. So that means that the covariance is 0, and thus the whole last term is 0. So what are we left with? Beta 1 is equal to delta 1 in from the long regression plus delta 2 times the covariance between chocolate and rich divided by the variance of chocolate. And if you look very closely at the last fraction, you can see that this is actually just the coefficient from a regression of rich on chocolate. So if we call this theta, whatever we get out of there, what we will end up with is exactly the famous omitted variable bias formula.
All right, we've got a long way now. We've got the OVB formula. What does this formula tell us? Why is it so useful? Well, it tells us that when we can estimate the short regression and still get the true effect of chocolate on rich. When would that be? Either if being rich does not affect a country's chances of winning the Nobel Prize, which is the case whenever other than through its chocolate consumption. You can check our graph from earlier, that's delta 2. Or if being a rich country has no effect on a country's chocolate consumption. If either of these conditions are true, then the short and the long regression give the same effect for chocolate consumption on winning a Nobel Prize. In the classical ordinary least squares assumptions, a very important assumption is that the error is at least uncorrelated, if not independent, of the explanatory variables that we use. If that's not the case, you have what econometricians call endogeneity, in which case you don't end up with the causal effect of these variables. You only end up with a prediction. Typically, we divide up endogeneity into three main sources. Firstly, omitted variables, which we've just looked at. Then into simultaneity, for which supply and demand is a classic example. And finally into measurement error. Neatly, we can represent the other two issues actually using our omitted variable bias formula. I leave this derivation in a supplement to this video. Alright, we've come a long way today. What should you remember from this video? Well, firstly, why is there omitted variable bias? Most importantly, omitted variable bias arises when we mistake the effect of an unobserved variable with the effect of an observed variable that is correlated with the unobserved variable. Secondly, the formula. You should definitely take away the omitted variable bias formula. From this, you know when you can rest safely when running your regressions, when you can expect problems, and actually it allows you to pinpoint where is the problem coming from. Finally, the visualizations. We looked at several different ways to see how omitted variable bias arises. If you can visualize these simple examples using either the graph network or plotting the data points, you see that actually omitted variable bias is quite intuitive. As you can surely imagine, omitted variable bias is a big problem if you want to do research. That's why there are a whole range of tools that econometricians have developed to solve these issues. If you want to get to know what these are and how they work, click subscribe below and check the other videos in my profile. There is also a related issue, which I mentioned in the beginning, the fundamental problem of causal inference. If you want to get deeper into applied research in econometrics and related fields, then you have to understand this one too. Check here for my video explaining the fundamental problem of causal inference. Thank you all for listening, and I hope to see you on my channel again soon.